Let's do one more lesson showing the utility of integration and solving some real-world problems. Have you ever played on a teeter-totter? Something that was fun during my day. Suppose you have two people that want a teeter-totter and they're the same weight. Then they just get on it and they teeter-totter back and forth. They're balanced. Well, what if you have one person who is, say, a mother or father who's here, let's make it like this, and say they weigh 200 pounds, and say they sit, well, let's do it like this instead. Let's say you've got the child over here that weighs, say, 50 pounds, and say they are 12 feet from the fulcrum. And now you've got the parent who weighs 200 pounds, and the question is how far should they be from the fulcrum so that these two balance, right? So that they can have fun teeter-tottering back and forth. And if you've ever played with one of these things yourself, you realize that, of course, the heavier you are, the closer you need to sit to the fulcrum. And it turns out that all you do is you multiply these two numbers to find, it's called the moment. It's not the weight, but it's the moment. So if you take 50 times 12, you will get 600 is called the moment on, say, going what's that, counterclockwise. And so you also need 600 foot-pounds going in the clockwise direction. So to get 600, you see that this person would have to be just 3 feet, right there. 3 feet from the fulcrum, and they're 200 pounds. And so each one adds up to 600 total, and you're all set. You can balance. Okay? So that's the idea. You can formalize this idea by talking about the moments in both directions and also the center of mass. So for example, suppose we have a bunch of weights on the x-axis here, and this is origin right here, and say this is x1 and distance x2 and distance x3 and x4, however we want, x sub n. Let's just say up to x sub n. Excuse me. And on each one of these, we hang a mass. So here the mass is m1, and here the mass is m2, and here m3, and here m4, and all the way up to mn. Okay, so there they all are hanging. And the question is, where would you put the fulcrum so that these things would all balance at just the right point, so that you could think of making a what's it called, mobile, where you want to tie the strings so that it all balances, or put a fulcrum so that they all balance. So what you're really doing is you're saying, well, let's just say it's right there. Say that's where called the center of mass is, and the notation we use for it is x bar, like that. There you go. So there's the center of mass. So what you want is you want the distance from each one of these things, x1 minus the center of mass, times m1, plus m2 times this distance from the center of mass, all the way out to the end, m sub n times x sub n times that distance. You want all that stuff to equal 0. So some of these things will be negative. Notice if you're on the left-hand side of x bar, then it'll be negative. If you're on the right-hand side, it'll be positive. So by the time you're done, it adds up to 0, which means that the contributions to the left exactly add up to the contributions on the right. So that's what you're after. So then we can multiply this all out and get m1 x1 minus m1 x bar plus m2 x2 minus m2 x bar all the way out mn xn minus mn x bar. There you go, and so that's set equal to 0. And now you take all these things and you keep those all where they are. Okay, let's use summation notation. That's the summation of mi xi, I going from 1 to n. That's the summation of all those. And that's going to be equal to, well, we'll bring all these negatives over to the other side. And when we add all those up, I can factor an x bar out in front of them all, and I'm just left with all the mi's, I going from 1 to n. So there you go. And so we notice then that the center of mass, you can actually find that by just taking this quantity here, which is the total moment, mi xi, I going from 1 to n, and dividing that by, notice that this is the total mass. That's the total mass right there. Just the summation of mi, I going from 1 to n. Okay, so let's put that up here. There's our formula. Okay, it's the summation of mi xi divided by just the summation of mi. I'll skip all the notation there and just leave there you go. Okay, so let's do an example. Suppose we have a bunch of things hanging on the x-axis as before. Here's 0 right here, and let's say that this is the point 4. I'll put the distances up above. So here's the point 4 right there, and here's 6 right there, and let's say that's 10 and 11 and say 15. Okay, there's all these distances, and here let's say that you've got a mass of 5, and here you've got a mass of 7, and here you've got a mass of 10, and here you've got a mass of 8, and here you've got a mass of, I don't care, 12. Okay, well, let's just make it something smaller so I don't have to multiply such big numbers. 3. Okay, so where will the center of mass be then? Where will the center of mass? So what do? The total moment, okay, we sometimes use a script m for the total moment, is going to be equal to 5 times 4 plus 7 times 6 plus 10 times 10 plus 8 times 11 plus 3 times 15. And what does that add up to? 20 plus 42 plus 100 plus 88 plus 45. And if you add all those up, let's do it real quick over here. 20, 42, 100, 88, 45. What does that add up to? There's 10, 15, carry the 1, there's 12, 13, 14, 18, 19, 295. So there's the total moment. And so the center of mass is going to be 295 divided by, I'm sorry, that's the total moment right there, divided by the total mass. What's the total mass? The total mass is simply 5 plus 7 plus 10 plus 8 plus 3, which is 12, 22, 30, 33. 33. So let me get a calculator for this. I've got one over here. Here we go. 295, 33, divide, and you get 8.9. 8.93. So if you were to want to balance it, you'd balance it right about there someplace. Around 8.93 is the spot. Okay? So that's the whole idea. So, as you might expect by this time, that's the kind of thing that you can do without calculus. But what happens if you have some sort of let's say we have the x-axis again, and let's say that it doesn't matter. Let's say from 2 to 8. Let's say we've got ourselves a rod. Okay, let's say we've got ourselves a rod. And let's say that the mass density of that rod, sometimes you use rho for mass density, is, let's say it's 3 grams per unit length. Okay, whatever these are, inches or something like that. Let's just call them all inches, okay? 3 grams per inch. So, if you have a rod there that's positioned from 2 to 8, and that thing is let's make it instead of 3, let's make it just trying to think of, let's make it 7 grams per inch, just so we get different numbers in there. Then where will the center of mass be? Okay, so let's figure it out. Well, okay, so the total mass of that thing, well, first of all, the total mass you could get pretty easily just by thinking, well, it's 7 grams per inch, and it's 7 times 5, so it's going to be 7 times 5 is going to be 35 grams, right? There's your total weight. Another way to get that is to say, well, you could say, well, okay, given a tiny little measure, a little tiny dx right there, then a little tiny unit of mass is going to be, for this little thing right here, I guess I'll use a capital M since I used a capital M up there. Oh no, I'm sorry. Let's let capital M be the moment, and let's let this be the mass. Okay. So here's what we're going to do. We're going to say, well, what's the weight of that little thing? The weight of that little thing is going to be 7 times dx, because this is the amount of grams per inch, and you multiply the grams per inch times the number of inches, which is a little dx, and there you have the grams. And then so the total mass is going to be what you get by adding up all of those contributions as x goes from 2 to 8. So notice the 7, you can leave it in there or bring it out front. Either way, you're going to get 7x when you find the antiderivative from 2 to 8. And you're going to get 8 minus 2 is 6. Let's see. This should have been a 6 here, right? 8 minus 2 is 6. Okay, I hope you were all yelling that. I didn't hear you, but that should have been 42. And the same thing here, right? 8 minus 2 is 6. 6 times 7 is 42. Okay? So there's the mass. Okay, that's fine. Now, what about the moment? What about the moment? Well, a little tiny piece of moment is going to be what you get by taking this mass right there. That mass is going to be 7 dx. There's the mass of it. And now I want to take that mass times the distance from the origin. So what's the distance from the origin? This is at the point x right there. So I would multiply that by x, just like I did in the discrete example. So there's the distance. It's at position x, so there's the distance. I multiply that by the mass of it, which is this right there, and that's a little tiny moment for that little piece. That's how much that little piece is contributing to the teeter-totter, to the seesaw. And now the total moment is going to be what I get by adding up all those things. So I'm going to get 7x dx from 2 to 8. And let's see, so what am I going to get here? I'm going to get 7x squared over 2 from 2 to 8. And so it's going to be, let's see, how can I make this as easy as possible? So I'm going to bring the 7 out front, and I'm going to leave the x squared over 2, so it's going to be 64 over 2 is 32, minus, that was when I put it in 8 here, 64 over 2. I put in a 2 here, it's going to be 4 over 2 is 2. 32 minus 2 is 30. 30 times 7. 30 times 7 is 210. So there's the moment. Oh, this one worked out kind of nicely, didn't it? I think. And so what's the center of mass going to be? The center of mass, oh, I guess that makes some sense. The center of mass is going to be the total moment, just like here. It's the total moment, which is going to be 210, divided by the total mass, right there, 42, which comes out to be 5. Okay, which is what you'd expect, right? You'd expect the center of mass would be right there in the middle, since it's nice and uniform. So I did a problem, but I did a problem very one that you could have done just by thinking about it without doing anything fancy. So now let's make this a more interesting problem. Now let's say that the mass density changes as you go. Let's say that the mass density is let's just say it's I don't care, is x squared grams per inch. Okay, in other words, it's made out of some sort of material that gets heavier as you go, right? It starts out light there, and then it's some sort of a metal alloy that just gets heavier and heavier as you go, or maybe it's thicker or something like that, so it gets heavier. So now that's your mass density now. So now what's everything going to be? Well, now, first of all, there's no easy way to do it. So now a little piece of mass is going to be, here's your little dx times the mass density. There's the mass density right there. So it's the mass density times the width times the thickness of it. And so there it is. And so the total mass is going to be, here's what you get by just adding all these things up. And if you do that, you're going to get what? 1/3 x cubed. Is that right? From 2 to 8. And again, let's see, what's 8 cubed? 8 times 8. 8 cubed is the same as 2 to the 9th. 2 to the 9th is 512. So it's going to be 512 minus 2 cubed, which is 8, all over 3, which is going to be 504 over 3, and 5 and 4 add up to 9, which is divisible by 3, so that means that 504 is divisible by 3. What is it? Goes in there 7 times, goes in there once, 3, you get 20, goes in there 6, 18, 24, 8. 168. Okay? So there's the mass of the entire thing, right there. Okay, there's the mass. Now, what's the moment going to be? Well, as before, the moment, what do? You take each one of these little pieces of mass. What's the mass of this thing? It's the same as you have up there. There's the mass of it. There's the mass of it, which is the mass density times the thickness. And now you have to multiply that by the distance away from the origin, which is going to be another x. So it's going to look like that. So this is going to be an x cubed dx. And what is that? Integrate to. It's going to be what? 1/4 x to the 4th from 2 to 8. 8 to the 4th is what? Let's see. 8 to the 4th, that's 2 cubed to the 4th, which is 2 to the 12th. 2 to the 10th is 1,024, so that would be 1,024 would be 2048, and you multiply that by yet one more, it's going to be 4096. So that's going to be 4096 over 4. Oh, over 4. So that goes back to 2024 again, or 1024. So it's going to be 1024 minus, if I stick in a 2 here, 2 to the 4th is 16. 16 over 4 is 4. So it's going to be just equal to 1020. Okay, you can check me out. Okay. Something there I want to get rid of. Uh-oh. What happened? Oh, I'm very good. Okay, just had some crazy stuff happen. Okay, so there it is. And so now, how do we find x bar? Same as before. It's going to be the moment. Here's the moment, which you get by multiplying the mass times the distances all over, which is 1020, all divided by 168. And that's nothing I'm going to do easily. I'll do that on my calculator. 1020, 168, and I get 6.07 approximately. So that kind of makes sense. You want an answer that makes, kind of rough sense, 6.7. You'd expect it to be over closer to this side because this thing is getting heavier as you go, right? That's a little closer to 8 than I would have imagined, but that's still reasonable, and I have no reason to. I think I did all my calculations right. So that's where you would balance it. Okay, that's where you would put a fulcrum, or that's where you tie it so that the thing would balance at 6.7. Okay, very good. Let's try one more. Let's jump from 1 dimension to 2 dimensions. And you can do quite a bit with this. The reason I decided to do this is because it's not quite as intuitive as working with volumes and surface areas and so on, but it's very, very useful. Whenever I taught engineers, then this is one of the most important things for them to know is, you want to balance a structure, and so you want the center of mass of something. The center of mass is basically where would you hold it, so you can think of the entire mass existing right there at that one point. Very, very important in any problems involving gravity or movement of any sort. So let's do this one. Let's do it over here, that you've got a triangle like this, where that's the top point right there, 1, 2. And so think of this as a flat piece of tin, okay? And we'll assume that the mass density of this thing is 1. So in other words, it's made out of a uniform material, and just to make it easy, we'll just assume it's 1. And basically, same as before, we want to balance this thing. But now the way we're going to balance it is we're thinking of taking this thing and finding the spot somewhere in the middle, so that if we wanted to drill a little hole there and put a thread there, that we could then have this thing lie flat, right? It's going to lie flat. Or if you wanted to, you could think of it as putting it on a little fulcrum, which is just a point, and this thing would just lie flat on the fulcrum. It wouldn't tip one way or the other. Where's the center of mass? What's the one point where we could put our finger there and it would balance right on our finger? Okay, that's what we're after. So now we have 2 dimensions to worry about, both in the x direction and the y direction. So first of all, let's do it first of all, let's find the mass of the thing. So the mass of it is going to be what you get just by basically finding the area. This is the line y equals 2x right there. Of course, this is 1 right there. And so the mass of it is going to be what you get by adding up all these little rectangles. Each one has height 2x, and the width of each one is dx. And I add all those up from 0 to 1, and you're going to get what? X squared from 0 to 1, which is exactly 1. So the area of that piece is 1, which of course I could have gotten just by, if you know the area of a triangle, it's 1/2 base times height, you're going to get 1. So that was easy enough. Okay? Now, let's find the moment around the y-axis, which means I have this rectangle right here. If I add up, think of all these rectangles as wanting to twist this thing into the board, okay, into the board around the y-axis, then what's going to be the moment? Okay, so the moment around the y-axis is what I get by, well, each one of those things. Here I am a distance x away. See that? I'm a distance x away right there. The mass of each one of those things is the 2x, there's the height of it, times dx. There's the area of that rectangle right there. And now what do? I take that mass and I multiply it by the distance away, which is another x right there. And so I add up all those contributions from 0 to 1, and we get what? Let's see, this is going to be 2. You have x squared, the antiderivative of x squared is going to be 1/3 x cubed from 0 to 1. And so you're going to put a 1 in there, you're going to get 2/3, put a 0, you're going to get 0, which is just 2/3. Okay, is that what I got before? I guess I didn't do it. Okay, so there's 2/3 right there. So, so there's your moment, and so then what's going to be the place where I would balance it along the x-axis so that it would balance? It'd be just the x coordinate of the center of mass is going to be just 2/3 divided by 1, which is 2/3. Okay, so it's going to be right out here someplace. Okay, so there's somewhere along that line. If I balance, I can balance it right along that line there where it's going to balance on both sides. Okay. Now, what about finding the moment around the x-axis? I need to do the same sort of thing. I've already got the area, I've already got the mass of it. But now I need to say, well, I've got some little rectangle there, and that little rectangle is going to want to pull it around the x-axis. So what's the moment due to that rectangle? Well, notice I'm going to have to, this is all in terms of y now. This is a little dy. So this is x equals 1 is this line right here. And this is the line x equals y over 2, right? If you solve that for x, you're going to get y over 2. So what am I going to get? It's going to be adding up. For this little thing right here, I want to get the area of it. The area of it is going to be this minus this. It's going to be 1 minus y over 2. There's that, times dy. That's the thickness of it, so that gives me the area. And now I multiply that area, which is the same as the mass, and I multiply that by the distance up. The distance up is just going to be y, like that. And I add up all those contributions from 0 to 2. And what do we get? we're going to get y minus y squared over 2 from 0 to 2 dy, which is equal to 1/2 y squared minus what? Y cubed over 3, and I'm already over 2, so it's going to be over 6 from 0 to 2. Put in a 2 right here, and you're going to get 4. 4 over 2 is 2. Minus, here you're going to get 8/6. 8/6 is the same as 4/3. 2 minus 4/3 is what? That's 6/3 minus 4/3 is 2/3. So there is, oh, interesting. So there is the, distance, let's see, we want how far up you have to be in order to balance it like this. So what do we do now? We go, what's the total moment? Here we want the y center of mass. It's going to be the total moment, which is this, divided by the mass, which is this. So it's 2/3 over 1, which is again 2/3. So they both end up being 2/3. So 2/3, 2/3. How interesting. So there you are. So 2/3, 2/3. Is going to be where that thing would balance. Okay. So there you go. So that's, anyway, that kind of shows you how this procedure can be used to find center of masses, both for something along a line and for something in the plane as well. So that's an introduction to it. Very good.